Hello Cloud Gurus! In this video, we're going to learn about the next iteration of big data tools that came out of the Apache Software Foundation, Apache Spark. So the MapReduce model was a notable advancement in computer science, and Hadoop enabled people to take advantage of this new programming paradigm to perform some impressive data analytics. These were the early days of big data, but as that data got even bigger, some limitations of MapReduce became apparent. Primarily, the issue was the linear flow of data. Every MapReduce job performed the same functions in order: read some data, map functions across that data, reduce the results, and write them to disk. Even though you could achieve some impressive results by combining multiple MapReduce jobs, don't forget this was the foundation of Google Search and PageRank, this linear constraint made it harder to run complex calculations without waiting a long time, even on large clusters of machines. In response to these limitations, Matej Saharia, while studying at UC Berkeley, created a new project called Spark, which was then open sourced and later donated to the Apache Foundation in 2013. Spark is designed to be a general-purpose cluster computing framework, allowing for concurrent computational jobs to be run across massive datasets. Spark uses the concept of resilient distributed data multisets, an extension of distributed storage, where data is replicated across multiple machines in a cluster but can be accessed as working sets of data by multiple jobs, without the iterative reading and writing to disk of the MapReduce model. In this way, you can think of Spark's storage model as a kind of distributed shared memory. Spark supports 4 standard modules, although there are also third-party projects that extend Spark's functionalities. The 4 standard modules are Spark SQL. This module is designed for working with structured data using a familiar SQL syntax. Structured data in Spark is stored in an abstraction called a data frame. For programmatic querying, developers can access the data frame's API rather than embed SQL into their code. Spark Streaming. This module allows you to configure streaming data ingestion in addition to batched processing. In reality, Spark Streaming uses very small batches to achieve this. The nice thing about this module is that you can use the same code for batch processing, join streams against historical data, or run ad hoc queries on the current state of a stream. MLlib. This is Spark's machine learning library, which supports all the machine learning algorithms you'd expect: classification, regression, decision trees, recommendation, and more. This is one area where Spark's iterative cluster computing stands out. In benchmarks, a logistic regression was 100 times faster on Spark than when using MapReduce on Hadoop. And finally, GraphX, a module specifically designed for iterative graph computation to save you the hassle of stitching together numerous MapReduce jobs. Spark supports the most common programming languages for big data, with libraries for Java, Scala, Python and R, as well as direct SQL support. To run Apache Spark, you need 2 things: a cluster manager and a distributed storage system. You have quite a bit of choice here. Spark will run as a standalone cluster, using Yarn on Hadoop, or even in Kubernetes. For distributed storage, Spark supports HDFS, as well as some structured storage systems like HBase and Apache Cassandra. To get a feel for how Spark is different to plain old MapReduce on Hadoop, let's take a quick look at a PySpark example. Once again, this isn't a follow-along lab. Just watch what I do, and it should hopefully help some of the theory we've been learning so far. Here I'm logged into a Compute Engine VM where I've installed Spark as a single node cluster. Even running on this single VM, I can configure Spark to run a single master and 4 worker processes. We can see this from the handy web UI that comes built in with Spark. Let's run a Spark job that gives us a bit of a glimpse of how powerful it is compared to a standard iterative MapReduce job in Hadoop. Spark comes with lots of example job scripts, including a basic implementation of Google's PageRank algorithm. Let's take a look at it in the Spark examples directory. I'll scroll down a bit to find the main function. So here we can see the script starts a session with Spark. The calculations that form the PageRank algorithm are then defined on the following lines. It's not too important to understand what's going on here, just that we're describing a set of steps to perform on the data in memory. When this job is submitted via Spark, the work will be distributed to all of the workers for parallel computation. So let's see it in action. I'm going to use a dataset that was released by Google as part of a coding competition way back in 2002. Let's have a look at the data. Each number in the first column represents the ID of a web page that has been linked to, and the number in the second column represents the ID of the web page where that link was found. The original dataset had over 5 million lines, but I've reduced it to 1 million for the purposes of this demonstration. It's still a sizable amount of data to map and graph. I'll just clear my screen. And now I can submit my job to the Spark master with the Spark submit command. I specify the location of the master, the job script, the name of my dataset file, and the number 10, which represents the number of iterations the algorithm should run on each web page ID. Each iteration will expand the number of neighbours in the map that its PageRank value is compared with. Now we've submitted the job, we'll get a lot of information on the console about its progress. We can also refresh the master web page to see our job as the current running application. While applications on Spark are running, they also present their own web page, which gives you a lot more detail and even some visualizations of the work in progress. Here we can see all the stages of our job, those that are active as well as pending. We can see that this job comprises several functions such as collect, reduce by key, and join. If we look at the active stage, we can see a graph visualization of the steps in this stage. Let's look at the executors page. Here we can see we're using 4 RDD blocks. This essentially means we're keeping all of our data in memory while we continually go over all of the stages on the data. This is a huge leap forward to the original MapReduce implementation of constantly writing intermediate data to disk and reading it back again. Let's have another look at the stages in our job. If we scroll down, we can see that some of the stages have completed now. Let's go back to our console and wait for our job to complete. A few minutes later, the job completes successfully, and the results are written to the terminal. Of course, if we were going to use this data for anything properly, we'd write it to a file or feed it straight into another kind of structured database. Here are all the calculated PageRank values for all of those web pages, although unfortunately we've got no way of telling what all these IDs actually refer to. There are some here with quite high numbers, so it would be interesting to know what they were. So to summarise, the main difference between Hadoop and Spark is the way that data is processed during computations. In Hadoop, data is stored in blocks on disk before, during and after a computation, which means that complex tasks involving multiple MapReduce jobs can be slowed down by lots and lots of disk I/O. Spark, on the other hand, stores computations in memory where possible, which, as well as being much faster, also permits multiple operations to be carried out on that data in parallel. In terms of latency, this makes Hadoop a high latency system and Spark a low latency system. There are a few cases where, to save costs, and if time is not an issue, you could use Hadoop for batch processing because disk is cheaper than RAM. But if you need streaming support, use Spark. In general, if you can afford it, use Spark. It's been shown to be 100 times faster at in-memory calculations and 10 times faster at on-disk calculations than Hadoop. Having this high-level knowledge of these differences will help you later in the course when we come to look at Cloud Dataproc, which is essentially a managed Spark service. Well, that's it for this video, Cloud Gurus. If you have any questions, please let me know in the course forum. I'll see you next time.